Hello. In this video, we are going to perform two calculations involving Wien's displacement law. And the significance of the law is that if we have a radiating black body, an object that's giving off radiation, the maximum wavelength of that radiation times the temperature will be equal to 1/5 of the C2 constant, where this C2 constant has the value of 1.44 centimeters Kelvin. If we substitute into the equation, we can actually come up with a slightly more useful version. Since we can put a 1.44 centimeters Kelvin divided by 5, we are able to simplify the right-hand side to 0.288 centimeters Kelvin. So, for our first calculation, suppose we have a black body radiator that's radiating with a maximum wavelength. Let's emphasize this just by putting a subscript of max, and it happens to radiate a maximum at 576 nanometers. What we would like to calculate is the temperature of this particular emitter. So we notice that with our equation we can solve for T, because we can notice that if we divide both sides by lambda, we can solve for T. So we see that the temperature is going to be equal to 1.44 centimeters Kelvin divided by the wavelength, which is 576 nanometers. We notice that 1 centimeter is 10 to the minus 2 meters, equal to 1 centimeter. And 1 nanometer has a length of 10 to the minus 9 meters. So if we include the two conversion factors to the right, we notice that the units of nanometers will cancel nanometers, the units of centimeters will cancel centimeters, and the units of meters will cancel meters, and we're left with an answer in units of Kelvin, which is exactly what we want. And when we do this, we get 5,000 Kelvin. So what this tells us is that if we have a black body that gives off its maximum radiation at a wavelength of 576 nanometers, what that tells us is that this particular object is at a temperature of 5,000 degrees Kelvin. Now, let us suppose that we have an object that is at a temperature of 4,000 degrees Kelvin. And what we would like to determine is, what is the wavelength at which the maximum amount of radiation is going to be emitted. Again, to use that, we need Wien's displacement law, which we recall is lambda max times the temperature is equal to 0.288 centimeters Kelvin. So if we substitute into the equation, dividing through by the temperature, we see that the maximum wavelength is going to be 0.288 centimeters Kelvin divided by the temperature of 4,000 Kelvin. And to convert to proper units, we notice that 1 centimeter has a equals 10 to the minus 2 meters. And we also notice that 1 nanometer has a length of 10 to the minus 9 meters. And we want to do a double check. We notice that our unit of Kelvin will cancel Kelvin. Units of centimeters will cancel centimeters. Our units of meters will cancel meters. And we'll be left with the units of nanometers, which is the units that we want for our answer. And if we do that, and solving using the powers of 10, we see that the maximum wavelength will actually be 728 nanometers. So what that means is if we have an object, perhaps a star, and the temperature is 4,000 degrees, light will be emitted over a range of wavelengths, but the maximum output of light will be at a wavelength of 728 nanometers. Thank you very much for your attention. Have a good one.